Hello everyone, I'm Yu Tang from LaAlO3 Research Group at the University of Pittsburgh. Today my topic is non-Coulombic long-range frictional drag in coupled lanthanum-illuminated strontium titanium nanowires. Frictional drag experiments involved closely spaced but electrically isolated conductors driving currents through one conductor called drive conductor, a voltage will be induced in the other conductor called drag conductor if it's open, or current will be induced if it's closed. From this phenomenon, the scattering between charge carriers into different conductors can be understood, and this can provide us additional insights into microscopic properties of interacting many-body system. Therefore, frictional drag is a powerful technique to study electron correlations. Previously, a lot of experiments have been done on 2D frictional drag, which involve two conducting layers. 1D frictional drag should be more interesting because electrons confined at one dimension are expected to have strong electron correlations. A lot of exotic behaviors have been observed with 1D frictional drag, for example, Wigner crystallization, latent liquidity effects, and so on. Previously, most 1D frictional drag were done on gallium arsenide system, and dominating interaction is Coulomb interaction. Complex oxide is a good platform to study electron correlations. The system we are working on is lanthanum-illuminated strontium titanium heterostructures. When a thin layer of lanthanum-illuminated is grown on top of strontium titanium, a 2D electron liquid will form at the interface. This interface exhibits a lot of interesting properties such as tunable metal insulator transition, tunable spin-optic coupling, tunable superconductivity, and tunable ferromagnetism. All of these properties are tunable, which give us more control over the interface. In our lab, we developed a technique called conductive FM lithography, which allows us to create nanowires at the interface. When 3 niche cells of lanthanum-illuminated is grown on top of strontium titanium, the interface is insulating. However, by applying a positive voltage to the conductive FM tip, one can locally make the interface conducting, and we can create nanowires. The typical width of nanowire is seen as 10 nanometers, and by properly control the clip voltage, it can be further reduced to 2 nanometers. This is a reversible process, therefore by applying a negative clip voltage, we can erase the nanowires and create various nanostructures such as quantum dots, quantum point contacts. High quality nanowire can facilitate. It's important for studying electron correlations. In our lab, we have proved to be able to fabricate electron waveguide where we can observe quantized transport, which confirms high quality of the nanowire in our system. We are able to fabricate a nanowire-based single electron transistor, and by performing experiments on single electron transistor, we discover a new electron phase where electrons pair without forming superconductivity. We also discover tunable electron-electron interactions in this platform. High-quality nanowire can facilitate the 1D frictional drag experiment as well. The geometry is straightforward. We have 2 parallel nanowires, each contacted using a 4-terminal geometry. The typical dimension of the device includes length range from 100 nanometers to 10 micrometers, width approximately 10 nanometers, separation from 30 nanometers to 1.5 micrometers. According to the testing at 50 mK, the wire distance is much smaller than interwire distance. Therefore, we can guarantee there is no leakage between 2 nanowires. Measurement is done by sourcing current in one nanowire and then measure induced voltage in the other nanowire. During the process, the other nanowire is open. For example, in this configuration, current I1 is sourced in wire 1 with a voltage Vs1, and we measure induced voltage V2 in wire 2. We can also measure the terminal voltage V1 in wire 1. The resistance given by this equation, for example, R21 is given by V2I1 the drag resistance, and the 4-terminal resistance. R11 is given by V1I1. If we source current in the other nanowire, we can get the other 2 terms. First, we show some typical drag resistance data. We started with high magnetic field regime where magnitude of magnetic field is larger than 0.4 Tesla, and nanowires are not superconducting. Magnetic field is applied perpendicular to the interface. On the right, the typical drag resistance as a function of magnetic field and the sourcing current. You can see drag resistance is antisymmetric in sourcing current, and it's magnetic field dependent. In some cases, the magnetic field dependence can be so strong that the drag resistance can change sign at different magnetic fields. To understand the coupling between two nanowires, we extract drag resistance as a function of separation between two nanowires from different devices. Separation ranges from 40 nanometers to 1.5 micrometers. And we claim the dominant interaction is non-Coulombic in nature. The reason is that if interaction is Coulombic, we expect drag resistance to exponentially decay as separation increases. But obviously that's not what we observe in our experimental data. Second, strontium tantalum is known to have a dielectric constant larger than 10,000. And with that huge dielectric constant, we expect the drag resistance to we expect the Coulomb interaction to be severely suppressed. But the drag resistance we observe is at the same order as previous data in the semiconductor system. So based on these two factors, we claim the dominant interaction is non-Coulombic in nature. We also perform triple Y experiment to rule out the device variance and study the separation dependence directly. The geometry is also straightforward. We have three parallel nanowires, each is 1.5 micrometers long and 750 nanometers apart from each other. Experiments were done by sourcing current in one nanowire and measuring induced voltage in the other two nanowires simultaneously. All three nanowires are grounded during the process. So to study the separation dependence of drag resistance, we fix the drag wire but the source current in different nanowire. For example, in these two configurations, we measure drag resistance. We measure induced voltage in wire 1 and source current in wire 3 and wire 2 respectively. We can look at drag resistance and we find they look really similar to each other. To compare the magnitude, we take the average over the positive bias and plot them together, and we can see despite the doubling of the separation, the drag resistance are almost the same. Therefore, triple Y experiment directly proves the weak separation scaling of drag resistance and the non-Coulombic nature of the interaction. What's more, if we focus on this configuration, grounding wire 2 should screen the interaction between wire 1 and wire 3, and we shouldn't actually observe any drag signal. But surprisingly, we still see a significant drag signal. Therefore, both the absence of separation scaling and absence of this screening effect proves the non-Coulombic nature of the interaction. The weak separation scaling of drag resistance also suggests the anisotropic nature of the interaction, because if the interaction is isotropic, as separation gets larger, we would expect less energy to be able to transfer between two nanowires, and we should have a stronger separation dependence. We also explore the superconducting regime where temperature is smaller than 200 millikelvin and the magnetic field is smaller than 0.2 Tesla. And different from high magnetic field regime where drag resistance is anti-symmetric with sourcing current, we can see the drag resistance in superconducting regime is asymmetric. Therefore, we can identify a symmetric component in drag resistance at superconducting regime. We find that this symmetric component of drag resistance is related to a superconducting normal transition in the sourcing wire. First, we show the two-terminal resistance of sourcing wire, which is wire 2 here. We can identify two pairs of peaks. The smaller peak is related to the superconducting normal transition in the nanowire, and the peak at the larger current is related to the superconducting normal transition in the leads. And clearly, we can see at the corresponding superconducting normal transition current value, symmetric drag resistance shows up for both nanowire and leads. And if we extract the magnitude of symmetric drag resistance at corresponding current value, we can see they are also separation independent. Therefore, the coupling is also non-Coulombic in nature in superconducting regime. To sum up, we perform one differential drag experiment at the lanthanum luminate strontium titanium interface. A non-Coulombic electron-electron correlation is revealed based on weak separation scaling. We perform triple wire experiment which directly proves the weak separation scaling and non-Coulombic nature of the interaction. In superconducting regime, we can identify a symmetric drag resistance which is correlated with symmetric superconducting normal transition in the dry wire, and the interaction is non-Coulombic nature in this regime. Thanks for your attention.